In this video, we're going to take a look at some of the basic concepts and terminology related to the process of integration. One of the most fundamental concepts related to integration is that of an antiderivative. Given a function f of x, we're going to call a function capital F of x an antiderivative of f of x if the derivative of capital F is equal to f. In other words, we're looking for a function capital F whose derivative is our given function. By convention, we'll always use a capital letter to denote the antiderivative of a function represented by a lowercase letter. For a simple example, let's look at the function f of x equals x squared, and let's suppose we're asked to find an antiderivative capital F of x for this function. In order to do this, we need to find a function whose derivative is x squared. Thinking back to our basic rules of differentiation, we should be able to pretty quickly come up with the function x cubed divided by 3 as a function whose derivative is x squared. We can take the derivative of this function, and applying the power rule, we obtain 3 times x squared divided by 3. And of course, the 3's cancel, and we're left with just x squared, which is our function f of x. Justifying that this is indeed an antiderivative of x squared. Now, it's important to realize that x cubed over 3 is not the only antiderivative of x squared. In fact, I could add any constant to x cubed plus 3. For example, I could add 5 and produce a different antiderivative. If I then take this new function f of x, capital F of x, and I differentiate it, we still get x squared. The derivative of a constant 5 is, of course, 0. And so x cubed over 3 plus 5 has a derivative x squared, and therefore it is also an antiderivative of x squared. To see another quick example, let's suppose g of x is equal to cosine of x, and we wanted to find an antiderivative, capital G of x, for this function. In order to do this, we think back to our elementary derivatives, and we realize that the derivative of sine is cosine of x. And so one possible antiderivative would be the function sine x. But as we just sort of saw in the first example, we could add on any constant that we wanted to this and still obtain an antiderivative for lowercase g of x equals cosine of x. The ability to recall basic antiderivatives, such as the two examples here, will be crucial as we go through our study of integration in future videos. Our first type of integral that we're going to consider is called an indefinite integral, and it's simply the collection of all antiderivatives of our function. When we write down the integral of a function f of x, that function f of x is referred to as the integrand of the integral, so that is our function that we're integrating. And in order to evaluate our indefinite integral, we simply need to find an antiderivative, capital F of x, of that function, and then add an arbitrary constant c to it. Whenever we write down an indefinite integral, it's going to be important that we include a differential at the end. Here, the dx indicates that we are integrating with respect to the variable x. If our function were f of t, then we would include the differential dt to indicate that t was our variable of integration. So for a couple quick examples, we can consider the same two functions that we found antiderivatives for on the previous slide. If we want to find the indefinite integral of x squared dx, we simply find an antiderivative of x squared, and as we've previously seen, x cubed over 3 will work. And then we add an arbitrary constant c to that function to obtain our collection of all antiderivatives, or the indefinite integral of our function x squared. For our second example here, we want to find the indefinite integral of cosine of t dt. Notice that we are using the variable t here instead of x, and therefore our antiderivative should also be with respect to t. We know that an antiderivative of cosine is sine, and so we can simply take our function sine of t, add our arbitrary constant c to give us our indefinite integral for cosine t. The second type of integral that we're going to discuss is called a definite integral. Unlike an indefinite integral, which is a collection of functions, a definite integral is always going to be a number. And that number is found by computing a Riemann sum of the function along the interval from a to b. Those numbers, a and b, are called the limits of integration. A is called the lower limit, and b is the upper limit, as shown by their placement along the integral sign. If we wanted to actually evaluate a definite integral from a to b of some function f, using the Riemann sum definition of the definite integral is going to be incredibly tedious, even for very simple functions. Fortunately, we have a technique that will allow us to compute most definite integrals very easily, assuming we can find an antiderivative for our integrand f of x. This technique is called the Fundamental Theorem of Calculus. This result says that in order to evaluate the definite integral from a to b of f of x dx, what we need to do is find an antiderivative, capital F of x, for that function. This can be any antiderivative. And we simply evaluate that antiderivative at our two limits of integration, a and b, and then we subtract those values. So our definite integral from a to b of f of x is going to be capital F of b, our antiderivative evaluated at the upper limit of integration, minus f of a, the antiderivative evaluated at our lower limit of integration. This will hold as long as our integrand f of x is continuous on the closed interval between a and b, which is the case for most of the functions we'll consider. Let's take a look at a couple basic examples using the Fundamental Theorem of Calculus. In our first example, we want to find the integral from 0 to 1 of x squared dx. To do this, we first need to find an antiderivative of our integrand. In this case, we've already seen that x cubed over 3 is an antiderivative of x squared. And we want to evaluate this function from 0 to 1. So we evaluate the function at 1. When x becomes 1, this is 1/3. We subtract from this the antiderivative evaluated at 0, which is 0/3 or 0. And so our definite integral here is 1/3 minus 0, which is equal to 1/3. So our definite integral from 0 to 1 of x squared dx is equal to 1/3. In our second example, we want to find the definite integral from 0 to pi over 2 of cosine t dt. The first step, as always, is to find an antiderivative of our function, and in this case, that would be sine of t. And we want to evaluate sine of t from 0 to pi over 2. So in order to do this, we find the sine of pi over 2, and we subtract from that the sine of 0. And we should know that sine of pi over 2 is 1, and sine of 0 is 0. And so the value of our integral here is equal to 1. While those two examples, hopefully made using the Fundamental Theorem of Calculus, seem very straightforward and very easy, there is one significant issue when using it to compute definite integrals. In order to use the fundamental theorem, we need to know an antiderivative of our integrand f of x, and for many functions, this is not always easy to do. For simple functions like x squared and cosine, an antiderivative is easily established, but there are many examples of functions whose antiderivatives are not easily determined. For example, let's say we wanted to compute the integral from 0 to 1 of x times sine of x dx. If we wanted to use the fundamental theorem of calculus on this integral, we would need to find a function whose derivative is x sine of x. And unless you've seen an integral like this before, you're unlikely to come up with such a function. And so without knowing an antiderivative of this function, there's really nothing we can do in order to evaluate this. And so one of the big topics in integral calculus is to come up with various techniques of integration in order to find antiderivatives for functions like x times sine of x.